Okay, so let's get started. As usual, don't forget the seating survey, Chem 112, Section 3, ILC 118. Only thing due this week is homework number 8, due it on Friday. The Friday office hours are canceled because I have to sit on a PhD dissertation committee during that time. So if you were planning on contacting me during Friday's office hours, feel free to send me a request for a separate appointment. I'm happy to get that set up. And as usual, 5 p.m. on Sunday is the Piazza participation cutoff for week 10. Next week, we should be back to our regular schedule with content videos. I'm working on getting those ready for you. Exam number 2, I posted a Piazza post that lists what the results of that exam were, as well as what the curves are for exams 1 and 2. Today, I will be getting up a walkthrough video on exam number 2. And so I will be, but I don't want to really open up questions about the specific questions on the exam until you've had a chance to take a look at that. One of the conclusions I came to from exam 2 was, while I really liked the idea of the kinetics simulation spreadsheet so you could make decisions on what experiments to run, I think in practice that having that on an exam was too stressful and too soon without enough practice beforehand going into it. So what I should have done is incorporated that into an activity rather than into an exam. And I apologize profusely for not having had that realization before the exam. The curve should help with that issue, and I'm not going to be doing something like that for future exams. That is off the table. I'm not going to have on any exam some new technology that's being incorporated that you have to try to figure out as you are working through the exam. So, with that said, do we have any logistical questions before I get on to content today? So, and before I say that, in terms of content, Monday and Tuesday, I went over the same material in both days. Because we don't have the content videos for this week, those 2 days were the lectures that introduced this week's material, which should have been sufficient to, plus the textbook, to get you through the Newton type homeworks this week. If you watched one of those 2, there is no reason to go to the other of those 2 because they were essentially duplicates of each other. I think that the Tuesday version was a bit more concise, probably because I'd practiced it on Monday. So you can get through the material a little more quickly on the Tuesday version if you still want to go back and do that. But now, having gone through that initial introduction today, my plan was to start addressing questions that people have on the material and on the Newton homeworks. Focusing first on the muddiest points that I've harvested from Piazza, and then anything we're doing, anything from the students here in class or remotely. So with that as prefaced, any logistical questions before we get into the content? Okay, so we had a couple of questions on pH and pOH. And so one of them was just asking for sort of what's the important thing to know about pH. The general idea of any P scale is that a P of anything is equal to the negative log base 10 of that thing. Okay, so for pH specifically, it is the negative log base 10 of the concentration of the H+ ion. And naturally, we can invert this equation so that we have our concentration of H+ equals 10 to the minus pH. So these are simply the same equation, just solved for different components in it. So what is pH? pH, very simply, is an alternate way to represent the concentration of the hydrogen ion. That is all it is. And we use it because when we are dealing with concentrations that are very small, tracking the scientific notation is that is involved in those concentrations can be a little more tedious than it is in dealing with a simple decimal number. So this kind of formulation can represent concentrations all the way from, say, 10 to the negative 14 up to 1, just by having a number that's a number before the decimal place with no scientific notation having to be involved at all. So that's the main idea of pH. Now, the second question we had here is, why have we never heard about POH before? Well, probably because POH, which is just like pH here, but POH is negative log base 10 of OH minus. It's probably because POH doesn't contain any new extra information compared to pH, because pH plus POH equals 14. And so you can specify the acidity or basicity of a solution just by specifying pH, because there is this relationship between the two of them. So, the practicing chemists then tend to pick just one of them to discuss, so you have this convention of always discussing a particular one, and pH is the one that has traditionally been picked as the one to do. Okay, any questions on pH or POH? Yes?
Is it possible to have a pH less than 0 or greater than 14?
Yes. Is it possible to have a pH less than 0 or greater than 14? Sure. So if you have a concentration of, let's say you have a concentration of the hydronium ion equals 1 molar. Okay. If that's the case, then our pH, that would be 1, isn't it? Let's say we make it 10 molar. If it's 10 molar, then that is 10 to the first, and so that would be a pH of negative 1. Okay. If you look at this in terms of this equation, that would mean your POH would be 15. Right? So that can in fact happen. It is very rare, but if you look at extremely concentrated hydrochloric acid, extremely concentrated sulfuric acid, extremely concentrated nitric acid, you can certainly get to stupidly high pHs, stupidly low pHs. And the same thing's true in the other direction as well. Although the components that contribute hydroxide tend to be less soluble than the components that contribute the hydronium ions. So it's not quite as wide a range as that you can have. Okay. Why does pH decrease with an increase in temperature? Okay, so the idea here is that our ideas of pH and POH started with our understanding of the reaction that is the autodissociation of water. And we said that this has an equilibrium constant of 10 to the minus 14 molar squared. And so if we look at the equilibrium constant expression for this, for neutral water, well, it's the equilibrium constant expression regardless of whether the water is neutral or not. But in the case where it is neutral, we have the same concentration of hydronium and hydroxide. And so that means that what do we need to square in order to get 10 to the minus 14? Well, it's going to be 10 to the minus 7. So our concentration of H3O plus equals our concentration of OH minus in neutral water, which equals 10 to the minus 7 molar. And so when we do look at the pH and the pOH, they become 7. Now, the problem is that this value for Kw is temperature dependent. So this 10 to the minus 14 value is the value of Kw at 25 degrees C. Don't know if this is going to be visible enough, kind of visible. Can people in the chat, can you see that at all, or is it too grainy? It's pretty grainy. Okay. So I will call out specific numbers that we'll talk about, and I'll write them in a little bit bigger. So this right here is 25. We have a Kw of 1.008 times 10 to the minus 14. I'm trying to not write over 10 to the minus 14, a pH of 7, and a pOH of 7. Okay. If we go to 20 degrees, then we have a Kw of 0.681 times 10 to the negative 14, a pH of 7.08, and a pOH of 7.08. If we go hotter by 5 degrees to 30, we have a Kw of 1.471 times 10 to the negative 14. We have a pH of 6.92. We have a pOH of 6.92. So it is always the case that the pH and the pOH will be equal to each other, but what their actual value is does depend on temperature sum. And that is because this is an equilibrium that we're looking at. It has an equilibrium constant associated with it, and the equilibrium constant is temperature dependent. Now, from this data that we have, we should be able to determine whether this reaction is endothermic or exothermic, right? So let's think about that for a minute. Let's see what you can come up with, whether this reaction should be endothermic or exothermic. There's a question in the chat, which I will come back to in just a second, but let's go through this part first. So what's the first question you ask if you're going to determine if this is endothermic or exothermic? Yes? Does the constant increase or decrease with temperature? That's right. So we see here that increasing the temperature from 25 to 30 increases the equilibrium constant. Decreasing it from 25 to 20 decreases the equilibrium constant. So increasing the temperature seems to increase the equilibrium constant. So what does that mean about which side we should put heat on in this equilibrium we've written? Yeah?
Put it on the reactant side.
On the reactant side. So heat plus on this side, which means that as we increase the temperature, we are increasing something that's on the reactant side, which shifts the equilibrium towards the right to the products. So if heat is on the reactant side, is this reaction endothermic or exothermic? The chat is saying endothermic, and that is correct. So yes, this is going to be an endothermic reaction because it requires heat for the reaction to proceed. It absorbs heat from the surroundings for it to move. Okay, so there was a question up above. In those cases, pH and pOH aren't adding to 14. This is correct. So when we wrote down here that, wherever I had that slide, when we wrote down pH plus pOH equals 14, that came from saying that Kw equals 10 to the minus 14. Oops, I'm not on screen. When we have pH plus pOH equals 14, that came from Kw being 10 to the minus 14. If your Kw is not 10 to the minus 14, then there's going to be some other relationship between pH and pOH based upon whatever Kw is. Okay. So you would have to have that information somewhere. This is a good example of a table that shows that information for what they are. And so for whatever temperature you're operating at, you would be able to determine what that equilibrium relationship is. Okay. So only at 25 degrees. Yes, that's correct. Okay, any clarifications on anything having to do with pH at the moment? Okay. All right. There was a great question asked on Piazza, and I think it's from a Newton question. How many molecules of water are dissociated in a sample of room temperature water? That is a great question, and let's see how we could figure that out. Well, the first thing we would need to know is how big a sample do we have? So let's say we've got a liter bottle of water. So 1 liter of water. And we are going to then need to have a concentration to multiply this by in order to determine what the how many molecules of water are dissociated. So we'll use this in a moment. Let's make ourselves an ice table, H2O. Actually, we don't even need an ice table because we know that at neutral, neutral water, we know that the concentration of the hydronium ions equals the concentration of the hydroxide ions, which equals 10 to the negative 7 molar. So that's where we start. If we look at the question, what am I trying to say here? If we look at the reaction for the autodissociation of water, so we have 2H2O is in equilibrium with H3O plus OH minus. Now, we have a subtlety we need to deal with here, which I think is a subtlety in the way the question is worded, and I would hope to not give a question that is going to have the same issue if we're doing an exam, because we could also write the autodissociation of water as H plus OH minus. And so remembering that H plus is a shorthand essentially for the H3O plus. So if the question is asking how many molecules of water are dissociated in a sample of room temperature water, do we consider both of these water molecules to be dissociated? Or are we really only talking about one dissociates, and then after the dissociation, the H plus ends up associating with an H2O molecule to make hydronium ion? The way I would interpret this question, though I admit that it is not a clearly worded question, the way I would interpret the question is that this is what we're talking about for dissociation, whereas this is a sum of a dissociation and an association step. And so this is the stoichiometry we would want to use, rather than this being the stoichiometry we would want to use. But like I said, I grant that the question wording itself is not completely clear on that point. But what this reaction means here is that however much our concentration of H plus or OH minus is, that is the concentration of water molecules that have dissociated. So we can simply take this number right here and say that is the concentration of water molecules that have dissociated. So we can take this concentration times this volume and say 10 to the minus 7 moles per 1 liter. We now have moles, but it's asking how many molecules are dissociated. So we then say we have 1 mole is 6.022 times 10 to the 23rd molecules. And then we just multiply it out. So this would end up being 6.022 times 10. What's 23 minus 7? Looks like it's going to be 16. So 10 to the 16 molecules in our 1 liter of water sample. Now, I understand that this question came from a Newton question, and I don't know what volume the Newton question asked for you to find this number of molecules in. So I don't know if I picked the right number here. But this is the general procedure you would follow to try to figure that out. Any questions on the autoionization of water and what it means in terms of concentrations? Okay. All right. How do we determine, a couple questions on amphoteric. How do we determine whether a substance is amphoteric? And I think the way the question was worded on Piazza, it was something like just by looking at the structure of the molecule that you're looking at. Well, I don't know that you can necessarily tell for certain, but there are parts of it that that you can look at that would give you some kind of indication. So the first thing is that it probably needs to have a hydrogen attached for it to be amphoteric. So you need to have some way for it to donate a proton. And then for it to be amphoteric, you need it to have some way that it can accept that proton, which usually means that you have some kind of lone pair for it to attach, for a hydrogen to attach to. So those would be two criteria I would look for in order to determine can something act as an acid or act as a base simultaneously. Now, simply having a hydrogen doesn't mean that, that it will be donating its hydrogen in any given reaction. So if we look at methane, for example, we've got hydrogens, but these carbon-hydrogen bonds are such that it would require one heck of a strong base to pull a hydrogen off from this because they're so tightly attached. So it is rare, it's not unheard of, but it is rare for a hydrogen attached to a carbon to be acidic in some way. And simply having lone pairs does not mean that whatever you're talking about can act as a base. So, for example, if we look at neon, we have lone pairs. But if we have a hydrogen plus coming up to it, it's really not going to form a neon hydrogen bond. And so this would not act as a base. So as you go through and practice a number of Bronsted-Lowry acid-base reactions, you may start to see some patterns in which kinds of bonds can act as hydrogen donors and which ones tend to not. So if you have a halogen attached to a hydrogen, then that hydrogen tends to be acidic. If you have a hydrogen attached to an oxygen, a hydrogen attached to a nitrogen, these can be acidic in certain contexts, though not in others. So for example, on the oxygen case, if we look at this molecule here, this is acetic acid. And this hydrogen right here is particularly acidic. But if we look at something else where the hydrogen is attached to the oxygen, such as ethanol, this hydrogen is not very acidic. I say very acidic. It is possible for this hydrogen to come off in some cases, but usually the equilibrium constant for that happening is tiny. So if you put a really, really, really strong base in here, it might be able to pull that hydrogen off. But it's quite rare for that to happen. So there aren't really very strong rules about what can be acidic and what won't be. There are some trends in that if you have a hydrogen atom that is attached to a particularly electronegative atom, then it is a candidate for being acidic. But other factors that we're not going to go into here would have to go into it to determine if it's going to be acidic or not. What lone pairs are good ones for pulling off hydrogens? Well, you typically need to have, the lone pairs will typically need to be on electronegative elements as well. So the same kinds of things that are more likely to hydrogen bond, for example. But it's not strictly that way. I mean, so there can be some cases with, say, sulfurs and phosphoruses and so on, which still are moderately electronegative, but they do not, they aren't electronegative enough for them to participate in hydrogen bonding. So the upshot is that you can sort of narrow the list of what the possibilities are, but you can't absolutely determine just by looking at it. Okay. There was also a question about amphoteric versus amphiprotic. Okay. So, and I'm wondering, does either the textbook or does Newton use the term amphiprotic in places? Okay. So I had missed that detail. So I certainly had not gone over this difference. The discussion that I just had about how do we determine whether some substance is amphoteric is actually better described as how to determine if a substance is amphiprotic. Because if we look at a Venn diagram here, amphoteric is a more all-encompassing term than amphiprotic. So amphiprotic is what we were just discussing, which is the ability of a molecule to act as an acid or as a base in different contexts in a Bronsted-Lowry sense. Amphoteric means a molecule that has the ability to act as either an acid or a base by any of the definitions of acid or base that we have, which includes the Lewis acid-base definitions, which do not necessarily involve the transfer of a proton. And so it is possible for a reaction to be a Lewis acid-base reaction without it being a Bronsted-Lowry acid-base reaction. And so it is possible for a molecule to be amphoteric but not amphiprotic. But if it is amphiprotic, it has to be amphoteric, because amphoteric encompasses all of that. I am not going to be emphasizing the Lewis acid-base definition very much, and I will only be looking at a handful of examples of Lewis acid-base behavior. And this is so that you are more familiar with, you are at least somewhat familiar with the concept of a Lewis acid base for when you get to organic chemistry, if you're going to go on and take organic chemistry. But I am not going to be asking for subtle distinctions having to do with Lewis acid base behavior. I will only be looking at sort of the broad ideas there. And that actually brings us to a question. I'm going to skip briefly the Bronsted-Lowry acid-base ones and come to the Lewis acid-base question that I have here, because apparently there is a question on Newton that has to do with coordinate complexes, that has to do with Lewis acid bases. So let me explain what's going on there, and to try to tie up the Lewis acid base idea, and then we can come back to the Bronsted-Lowry stuff. So remember from my introduction of Lewis acids and bases that I described it as essentially having a lone pair on one species, and we have some other species where, using the arrow pushing notation that I introduced in classes Monday and Tuesday, we show the movement of electrons, and we end up forming a covalent bond as a result of this. And so this here would be the Lewis acid, because it is an electron pair acceptor. This here is a Lewis base, because it is the electron pair donor. This species that we have here, where a covalent bond has been formed, is called a coordinate complex. What we mean by a coordinate complex is a molecule or polyatomic ion where a covalent bond was formed where both electrons came from, I've run out of space, came from the same reactant. Okay. So what you can see here is that both of the electrons that are forming this bond are coming from the X, and they end up as the two electrons that form that single bond. That's what we mean by a coordinate complex. This is distinguished from a case where we have X dot, Y dot, and you have one electron coming from each of the two components in order to form the resulting XY bond. So this one is not a coordination complex. Now, a subtlety, just so that I'm not throwing notation at you that you've never heard of. A subtlety here is, you notice that I drew these two arrows in my arrow pushing mechanism with only a single half of the head of the arrow. That is because that's what we do when the arrow is describing the motion of a single electron. So you think of the arrow as having as many barbs on it as there are electrons that are moving. So in this case, it's a double-headed arrow because it's showing the movement of an electron pair. Down here, it is a single-headed arrow, a single barbed arrow, because it is showing the movement of a single electron in each case. You are not going to be tested on that. That is something that is going to be introduced in more depth when you get to organic chemistry. I don't want you to be baffled by why I'm using the notation that I'm using. That's the only reason I'm bringing that up. Okay, how can we tell where the E-S comes from, the electrons come from, where it's a regular covalent bond and whether it's an acidic pair donated or accepted? So I don't know that you could look at just the species that you have and determine, is it a coordinate complex? I think you would have to know what it is coming from so that you would be able to draw the Lewis structures of what it's coming from and then envision where would the electrons have to go in order to form this bond to determine, is it a coordinate complex or not? Okay, any questions on Lewis acid bases, coordinate complexes, and what the electrons are doing in these cases, and amphiprotic versus amphoteric? For the purposes of this class, simply because I'm more used to using that word, I will almost always say amphoteric rather than amphiprotic. But because we are going to be emphasizing primarily Bronsted-Lowry definitions, when I say that, the examples I will be using will almost across the board be Bronsted-Lowry and therefore amphiprotic examples. So I do not anticipate asking you any questions about compounds that can act as both Lewis acid and Lewis bases. Okay, so let's go back now to, so we've done that, and we're going to go back to do some Bronsted-Lowry acid-base stuff. But I saw that I also printed something out here that someone posted to Piazza that is a very convenient sort of diagram that shows you how to convert various things. So H plus concentration, OH minus concentration, POH and pH, and it shows what all of the calculations are to go from one to another. If you understand the relationships such that OH minus concentration times H plus concentration equals the KW, then you can do the top one in your head without looking at, well, yeah, you need a calculator probably, but you can determine what you're needing to do on the top one without necessarily having the chart. If you know that the relationship between pH and POH, they always sum to 14, you probably don't need the bottom one to remind you what to do. And if you remember the definition of what a p-scale is, you probably don't need the vertical versions either. So, but nonetheless, this is a very sort of concise way to capture the various conversions that you do. So I thought I would point this out to you. And so if this is something that you think would be useful, go seek it out and make your own copy of it. Okay, let's go back now, and we will, how are we doing on time? We're doing great on time. Let's talk about Bronsted-Lowry acids and bases. So the first question is very simply, what is a Bronsted-Lowry acid and base? The general idea here is that the Bronsted-Lowry acids are proton donors and bases are proton acceptors. And when we say proton here, we are not referring to a nuclear reaction where the number of protons in a nucleus is changing. That is not what we're talking about. We are talking about the H+ ion, which is a bare proton. And so when an H+ transfers from one molecule to another molecule, that is an acid-base reaction under the Bronsted-Lowry definition. A key thing to recognize here, as I tried to emphasize the last couple of days, is that the Bronsted-Lowry definition is a fundamentally reaction-based definition. Something acts as a Bronsted-Lowry acid in a specific reaction. Something acts as a Bronsted-Lowry base in a specific reaction. You do not look at something, a compound, and say that is a Bronsted-Lowry acid, because you don't know the context of what reaction you may be talking about. Maybe it's something that's amphoteric, where it usually acts as an acid in reactions, but maybe there's some exotic reaction where it acts as a base. Or you may be talking about using it in a reaction where while in other reactions it would act as an acid, in this case, it's not actually giving up its proton, and so it's not acting as an acid in that particular reaction. So Bronsted-Lowry is about the function that the role that a compound plays in a reaction, is what we're looking at. Okay, any questions on the definitions of Bronsted-Lowry? Okay. There were a couple of Newton questions that people wanted me to go over specifically. According to the Bronsted-Lowry definition, what acts as the acid when the reaction below proceeds in the forward direction? So going from this side to this side. Let's think about our definitions. We have the acid in Bronsted-Lowry is a proton donor. So which species here is donating a proton in this reaction? Yes? HF. Because we see over here that the remainder of the molecule, the F-, is lacking the hydrogen that we started with, so it's the one giving it up. And by process of elimination, the H2O has to be acting as the base because it is accepting that proton that the HF donated, leading us to have H3O plus on this side. Okay, any questions on how to identify that? No? Okay. All right. Another example Newton question that people were having some trouble with. Which of the following will not participate in an acid ionization reaction? Okay, so we have seen examples already of HCl acting as an acid, donating its proton. Okay, we have seen HBr, given that Br is in the same group as Cl, we would expect HBr to act similarly chemically to HCl, and thus to give up its proton in an acid-base kind of reaction. And in fact, we see another example of that same group here where HF, where fluorine is also a halogen in that same group, acting exactly the same way. So with quite some confidence, we can say that HCl and HBr both participate in acid ionization reactions. What about water itself? Yes, the autoionization of water on its own is evidence that water can participate in acid ionization reactions. But we also know that water can participate in one of these reactions like this, and where it is acting as the base and pulling the hydrogen off of the acid. Or it could react as the acid if you put it in with a base where it loses one of its hydrogens to leave OH- behind. So, So water can clearly participate in one of these reactions. So the only one left is helium. Well, helium we know is a noble gas and thus does not participate in many reactions at all. And I don't know in Chem 111 how much detail you went into that particular aspect. If you look at the periodic table for the noble gases, there are a few compounds of radon that can be made. There are a few compounds of xenon that can be made. There are a couple compounds of krypton that can be made. They are all pretty exotic and not something you typically run into outside of trying to do complicated VSEPR examples is typically where you will find things like that. But I believe there are no compounds known with argon, neon, or helium. Okay. I know there are none known with helium. I know there are none known with neon. Argon, maybe there's one that I haven't kept up with the literature on that to know if anything new has been found. So helium, the reason we might think that it could potentially participate in an acid-base reaction is that its only shell you can think of as a lone pair. And so potentially you could imagine, let's say we have HCl, you might imagine this kind of thing happening. And so that's why you might think perhaps it could. But the thing is that these electrons are held so tightly to the helium that it's not going to want to share them with the hydrogen. And so this ends up not happening. So the answer here has to be helium, that is the one that does not participate in acid ionization reactions. Any questions on that? Okay, our last Piazza question is about conjugate acids and conjugate bases. So let's look at an example. I did acetic acid before. Let's do the ammonia reaction right now. NH3 plus OH, nope. I'm gonna start over, so I'm starting fresh here. NH3 aqueous plus H2O liquid is in equilibrium with NH4 plus aqueous, I never leave myself enough room, OH minus aqueous. All right, for the forward reaction as written here, what is acting as the acid, the Bronsted-Lowry acid? Yes.
Water.
Correct, water. What is acting as the Bronsted-Lowry base? Ammonia. If we look at the reverse reaction, starting with the NH4 plus and the OH minus, for that reverse reaction, what is acting as the Bronsted-Lowry acid? Okay, from the chat, NH4 plus. I'm sorry, I didn't speak up. So yes, the NH4 plus is acting as an acid in the reverse direction. So this is called the ammonium ion. And so by process of elimination, the OH minus is acting as the base for the reverse reaction. So if we are to think of an acid-base reaction in the Bronsted-Lowry sense as a proton exchange, then essentially what we're talking about is some species that can exist in two states, either with its proton or without it. And actually that's true for both of the species that are involved. So we have our NH3 that can either have an extra H plus or not, and we have an OH minus that can either have an extra proton or not. And so these species form what are known as conjugate pairs. NH3 and NH4 plus are a conjugate pair. OH minus and H2O are a conjugate pair. And so traditionally, whichever way our equilibrium reaction is written, we label the reactant side as the acid and the base, and we label the product side as the conjugate acid and the conjugate base. Okay. So a place where this comes into play is with thinking about the effect that different compounds will have on the pH of a solution. So let's look at apparently my favorite example, vinegar, acetic acid. So acetic acid, acetate ion, okay, water and hydronium. So noticing that our acetic acid, which is acting as an acid in this reaction, has a conjugate base of the acetate ion, tells us something about what happens if we make a solution of, say, sodium acetate. So this is just the non-Lewis structure version of this. If we make a solution of sodium acetate, then the acetate ions that are now dissolved in water are going to start participating in this equilibrium reaction. So we're taking a system where there's initially none of this, right? And we add in just the acetate ion. What's going to happen to the equilibrium when we do that? Which direction will it shift? Towards reactants, right? Which means that the H3O plus concentration is going to go down. And so the solution becomes basic as a result. So even though looking at this, it doesn't look like an Arrhenius base, it doesn't look like something like sodium hydroxide where, okay, we're making it basic because there are hydroxide ions we're putting in. Even though it doesn't look like that, we are putting in something that participates in an equilibrium that will cause the reaction to shift away from hydronium. Okay. Any questions on this concept of conjugate acids and bases and the information you get as a result of knowing that they're conjugates? Okay. The other thing you can do with conjugate pairs is that if you know the Ka for the acid, you can find the Kb for the conjugate base and vice versa. I did go through that yesterday and Monday, but I can go through that again if you would like. Otherwise, I am done with the Piazza Muddiest Point questions that came up, and so I'm happy to open the floor to any questions from anybody, if anybody has any. Do you guys want me to go through again the relationship between the Ka and the Kb of the conjugate? Seeing silence in the chat and some non-committal stares. All right, I will go through that. So here's the idea. I'm going to represent our acid as HA. And we are adding it to water. It is in an equilibrium with A minus aqueous and H3O plus aqueous. This general formulation is the acid reaction. Every acid reaction you have, you can put into this form. And so the Ka is going to be concentration of A minus, concentration of H3O plus over concentration of HA. Similarly, you can write a base reaction, which is going to be A minus aqueous plus H2O liquid is in equilibrium with HA aqueous plus OH minus aqueous. Any base reaction you can put into this form. And so the Kb is going to be, HA OH minus over A minus. So what's the difference between these two reactions? Well, obviously they're flipped, but we've also switched whether we're talking about water and hydronium or water and hydroxide. So that suggests that when we're going to flip these, we also need to take into account the autodissociation of water, which has a Kw of H3, I can't write, H3O plus OH minus. Okay. And so our Kw is concentration of H3O plus times concentration of OH minus. So now let's think about what we can do to manipulate these. If we take the top reaction and reverse it, what do we do to our equilibrium constant? If we take this and rewrite it so that the reactants are on the right and the products are on the left, what happens to our equilibrium constant? So I'm going to cover that up, and let me actually write it now. A minus aqueous plus H3O plus aqueous is in equilibrium with HA aqueous plus H2O liquid. I'm not going to call this a Ka anymore because we wrote the reaction backwards. I'm just going to call it a K. What's the K for this expression that I just wrote, for this reaction?
HA times H2O over A.
Well, we're certainly going to have HA. Do we include the H2O?
Oh,
Nope.
over hydronium times A.
Right there. What's the connection between these two? It's flipped. So this is equal to 1 over Ka, right? Now, we also have our Kw thing going on, right? Kw is concentration of H3O plus times concentration of OH minus, right? So I'm going to come over here now, and I'm going to solve this for the H3O plus. So Kw over concentration H3O plus equals, nope, I'm doing this backwards. Sorry. Kw over concentration OH minus equals concentration of H3O plus, right? I'm now going to take this and plug it in here. And so we get that the equilibrium constant for this reaction is going to be HA Kw, what am I doing? Hang on. Kw, concentration A minus, and up here, we are going to have the OH minus. And remember, this equals 1 over Ka. You with me that far? Okay. Now, let's also now look at our Kb reaction for the conjugate base. HA, OH minus over A minus. That's most of this right here. So what we have is Kb for the conjugate base over Kw equals 1 over Ka. And so just rearranging this a little bit, not on board, nope. Kb times Ka equals Kw. So for a conjugate pair, the product of the Ka of the acid and the Kb for its conjugate base equals Kw. So that lets you determine one of the two equilibrium constants from the other. Okay. Yeah, I see the complaint that you couldn't see. Were you able to see everything you needed to now? I saw and moved it up. Okay. All right. Any clarifications on the way conjugates work? All right, we have about 5 minutes left. Anybody have anything else you would like me to try to address? Yes?
I still don't really understand how you determine which one's going to be the reaction, which one's going to turn into the base, which one's going to turn into the acid. Because sometimes water is the conjugate for the base, and sometimes it's for the acid.
Right, so a little confusion over how to determine what's going to be the base and what's going to be the acid. So generally you'll be given the full reaction. Okay, so let me see if I can pick a different example from the ones we've looked at before. Let's say we have H2SO4 aqueous plus H2O liquid goes to HSO4 minus aqueous plus H3O plus aqueous. Okay, so you would be given the reaction typically. And so what you do is you look at what's happening in the process, and you see that the HSO4, that's coming from this part right here, but it's lost a hydrogen. And if you look at the charges, it's gone from neutral to negative, so it's lost an H+. So because it's lost an H+, it's the donor, so this has to be the acid. This is in fact sulfuric acid. If we look at the water, it's going from H2O to H3O, so it's getting getting a hydrogen. We look at the charges, it's going from neutral to plus, so it's getting the hydrogen in the form of an H+. And so it's the proton acceptor, and so is therefore the base. Okay, does that help? Okay. Anything else? Were there any questions yet in Newton on polyprotic acids, where an acid can give up more than one proton? No? Okay, so that's probably next week. Okay. Does everybody feel comfortable with the distinction between strong acids and weak acids, and strong bases and weak bases? Yeah, okay. And yet you all recognize that saying that something is a strong acid does not mean that there is a very high hydronium ion concentration. Okay. Trying to think about common pitfalls, and I'm not coming up with much. Okay, well, if nobody has any other questions, let's call it for today. Thank you very much.